Hello there, Steven here. I'll talk about this paper called WaferLLM, where they do large language model inference on a wafer scale silicon chip. So as background, this startup called Cerebras just scored lots of funding and is preparing for an IPO. As early as 2014, they've already made this chip that is huge. It is made using an entire silicon wafer, and this is the silicon part itself. For reference, it is about 30 centimeters wide and is a square. In comparison, a very large GPU would be this big compared to this second generation Cerebras wafer scale engine. And what this chip provides is tens of gigabytes of on-chip memory compared to tens of megabytes on the GPU chip itself. And GPUs also come with a high bandwidth memory attached to the silicon part that would be hundreds of gigabytes. And the on-chip memory bandwidth is tens of petabytes per second compared to a few terabytes per second or hundreds of gigabytes per second, either on the silicon or with HBM. So why do we need such high memory capacity and bandwidth? Well, latency. LLMs take a lot of time to produce their output, and many cannot wait. Some tasks even benefit from very fast output. So their goal here is to have a very low latency LLM inference. The way it works is they have inference on a single chip so that there's no cross-chip or cross-machine latency. And since inference is memory bandwidth bound, it should be very low latency overall. Although there are no cross-chip or cross-machine networking latency, they do have this new thing called a network on chip, which they need to deal with. To understand, let's look at how a chip would look like. At the bottom, you have the transistors and the gates, and you have layers upon layers of wires on top. So this means big chips cannot have random access to its memory because there will be so many wires on top, the chip will be thick and unable to cool. Instead, Cerebras made a mesh of tiny computers in their chip. So the chip will look like this, where this would be the silicon wafer, which is circular, and the chip itself is square, as we saw. On the chip, there's a mesh of cores. This is a core, each with tens of megabytes of memory, and has a router that can accept data from other cores and send it elsewhere, and obviously has compute like a GPU. This chip has network on chip that works like a mesh, where each chip can have data from neighboring core. Each core can have data from each neighboring cores. That means sending data to your neighbor is one hop away and very fast. But sending data to all the way across the chip would incur thousands of times of latency because it would need to cross each core one by one. by the way, this is not a new architecture. The core mesh architecture has been very old, and people have done that with specific instructions to send data to neighboring cores. Here, instead, they have a label switching. Basically, the chip can produce a message that contains a 5-bit label. And it does label switching like software-defined wide area network in Microsoft, where they will have 32 routing paths at most per core, and the core would use a table to decide where a message should go once it receives it. If 32 is not enough and we are out of routing paths, we must either reprogram the chip or we need to send the data off the chip, which would be slow, and we need to avoid that. So that was the chip. Now about LLM inference, the main tasks are prefill, decode, and KV cache management. For prefill, we are basically doing parallel generic matrix multiplication, or GEM, where we load up the context and load them into the model in parallel. Decode is where we produce the tokens one by one sequentially using generic matrix vector multiplication, or GEMV. The reason why the paper uses GEMV instead of GEM is they are using batch size equals 1 for minimum latency. We note that in real life settings on GPUs, you will have a much higher batch size for overall throughput, and you actually use GEM for decode as well. The paper also talks about KV cache management, which I will not go into here. So the goal here is to minimize the following. First, we have the maximum routing paths per core because we want it below 32, otherwise it won't work. We also want to minimize the maximum latency, or basically hops, between cores each step would take, because the slowest part of the step, the straggler, defines how much latency each step takes. And finally, we need to minimize the maximum memory we need per core, because otherwise it won't fit. So for GEM, what we are doing here is we are multiplying a bunch of numbers, and then we are adding them together, accumulating them. So what we really need, we need to shuffle data around efficiently. And the idea here is we can have circulated data per row and per column. The paper compares traditional GEM and other GEMs optimized for Cerebrus chips. And they all have these problems where either they have long routing paths, latency, and they take much memory in the traditional GEM's case. WaferLLM proposes this kind of routing path where you will skip by a core to go to the right, and once you come back, you skip by a core. By the way, it doesn't have to be 5, it can be much longer. This is just an illustration. So to be more concrete, you have slices of matrix A in this row and slices of matrix B in this row. And you'll circulate these slices around. And this row will contain other parts of A, other parts of A, other parts of B, other parts of B, etc. So you could have n cores here, n is 5, cyclic data flow, and you have logical cycle, but when you squish it down, you have 2 hop steps. So the maximum latency is the 2 hops, and you're basically using 2 of the labels in your routing. MeshGem, however, needs to replicate and partition tensors on different dimensions and propose a K-tree all reduce to aggregate all the local results into a final result. This is similar, but instead, what they need is all the data in one place. So what they propose here is they have a tiered system where all the cores first send data to half of the cores and then send data to half of cores and finally reach one core. And in this way, they sacrifice the simple routing. They need to take K route paths for the K tree, but they reduce the latency. So to evaluate how these MeshGem and MeshGem work, they propose an unusual metric, which is the throughput per request, defined as the inverse of time per output token, basically inverse latency. As notes here, the 34 billion model and the 72 billion model didn't fit on the chip, so they scaled up the result from a subset of layers, which is questionable. First, they presented the inverse latency for prefill, and these are the models they've used, A13, 34, and 72 billion parameters. And they first compare their methods to other methods that also target Cerebrus chip. As you can easily see here, inverse latency is much higher for WaferLLM compared to all the other methods by a lot. And as they use more cores, the inverse latency only went up. Even compared to the GPU, these performances are still much better, around 1 or 2 times. When it comes to decode, the story is much different. WaferLLM can produce 10 times the inverse latency compared to GPU options. As you can see here, having more GPUs on one machine makes decode faster, but having more machines make the decode slower because of network latency. And here, we can see more cores being used increases the latency on Cerebrus chip. But overall, we can say that the inverse latency in the evaluation is much higher in preview for Cerebrus chip and WaferLLM, especially versus multi-node, and is 20 times higher in decode. And to explain that, the authors plotted the cycles versus how many cores are being used on the chip. So basically, Cerebrus implementation has a linear growth of number of cycles versus how many cores on the chip they use. But WaferLLM's MeshGem only uses a relatively constant number of cycles. And since GEMV is mainly communication overhead, Mesh GEMV is much faster and scales much better. Finally, we have some criticisms that I would want to throw out on this paper. First, the paper said they couldn't even fit a 34 billion parameter model, so larger models and likely large KV cache likely cannot fit on the chip. That makes the chip much weaker because smaller models are limited. Second, it seems like they're assuming the chip only serves one user at a time, which may be very unrealistic most of the time in real workloads. And we'll probably see very high cost per request compared to GPUs, which does large batching. And as for the larger model doesn't fit problem, we can see the on-chip memory between the second and third generation Cerebrus chip is not very big. So we are not getting that much more memory, and this problem probably would not be solved, and we will have to shift memory on and off the chip anyways. But besides that, there you have it. We have the low latency wafer scale LLM inference implementation, WaferLLM.